The learning goal for this video is I can apply Newton's universal law of gravitation. So let's see what that means on a conceptual level. I have two masses here. There's going to be a force of gravity on each one of those masses. And notice the force of gravity is attractive. Now we can increase that force of gravity. So this arrow shows the force. I can increase the force by increasing one of the mass, but look what happens to the other force as well. It also increases. So this is Newton's third law. For every force, there's an equal and opposite reaction force. So I can increase the mass, which increases the force, or I can change the distance between them. The farther apart they are, the weaker that force is going to be. So let's see what that means in an equation. Increase one of the masses, either one of the masses, the force is also going to increase. Or I can increase, r is the distance between the centers of the two objects. If I increase that number, this force is going to decrease. Those are inversely related. Let's see how we can apply this law. G is a constant. So we'll talk about that constant in a second. All right. So I'm going to only answer the odd number questions from your worksheet. And this one says, at what distance apart would two equal masses of 150 kilograms need to be placed for the force between them to be that value? So the force is going to be the force of gravity. G, m1, m2, all over r squared. So we're applying this formula. So we want the force between them to be 2.0 times 10 to the negative 5 newtons. G is a constant. You can find it with your data up at the top here. 6.67 times 10 to the negative 11 newtons meters squared kilograms to the negative 2. Two equal masses. So each one of those masses is 150 kilograms. And we need to find what is that distance between them. What is r? So we can get r by itself by multiplying both sides by r squared. And that gets rid of the r squares on this side. And then the next step would be to divide both sides. Now I'm left with, if I divide both sides by this value, I need to divide it over here as well. That gets rid of this value. What I'm left with, r squared is equal to 6.67 times 10 to the negative 11 times 150 times 150 divided by 2 times 10 to the negative 5. Need to take the square root of both sides, and I'm left with my answer. You put this in your calculator and you find it to be 0.27 meters. Okay, in this question we want to show that the units for G, that's the constant, can be expressed as this. That should say squared. So, we see back here. Here are the units for G. How did it, you're probably going to forget that those are the units for G. So I'm going to show you a method that you can use to always remember the units of pretty much anything. So it starts with thinking of an equation that has that unit in it. So an equation that we have is force of gravity is G, m1, m2, all over the distance squared. So we want to know the units for this. So we can use the units that we know for the other variables. So force of gravity, a force is measured in newtons. G, well, that's what we're trying to find out. We're not sure what those units are. Masses, well, they're each measured. Standard units are kilograms. And distance, I have meters, but there's a square there. So let's get question mark all by itself. When I get question mark all by itself, I have to multiply both sides by meters squared. So I'm going to have newtons, meters squared, and then I have to divide both sides by kilograms times kilograms. I can just say that is kilograms squared. So another way we can write this is newtons, meters squared, kilograms to the -2. So these two are that's just another different way of writing units. In this question, we want to show that the pull of the sun on the moon is about 2.2 times larger than the pull of the Earth on the moon. All right. So the pull of the sun on the moon. Well, that's the force of gravity from the sun on the moon is equal to G, mass of the sun, mass of the moon, divided by the distance, and I'll just write sun, moon squared. So we can put in our values, see what we get. Mass of the sun, 2 times 10 to the 30 kilograms. Mass of the moon, 7.322 kilograms. And the distance. So let's try to draw a picture to figure out what the distance from the sun to the moon is. So we have the distance from the Earth to the sun, and the Earth to the moon, but we don't have any sun to the moon. So if I draw a picture here, let's have the sun. Here I've got Earth. And the moon can be, well, it can be on either side of the Earth or anywhere in between. So it can be over here, or it can be over here, or it can be anywhere in between. But let's try to figure out some of these distances to figure the distance from the Earth to the sun. Is 1.5 times 10 to the power of 8 kilometers. The distance from the Earth to the moon is 3.8 times 10 to the power of 5. And this, similarly, that distance, 3.8 times 10 to the power of 5. So the distance from the sun to the moon is either 1.5 times 10 to the power of 8 minus this value, and that will give me my remaining distance, or it's 1.5 plus this value, or it's anywhere in between those two values. So hopefully you can see that the distance to the moon, or sun to the moon, is going to be, well, 1.5 times 10 to the power of 8, either minus, so that would be this distance, minus 3.8, put that in the calculator, and this rounds to, well, approximately it's almost the same. It's 1.496 times 10 to the power of 8. And the maximum distance it can be is 1.5 times 10 to the power of 8. Look, I have to add these two values together to find this total value. Plus 3.8 times 10 to the power of 5. If you were to put that in your calculator, you would get 1.504 times 10 to the power of 8 kilometers. So look at these two numbers. I mean, if we were to round, we could say this is about 1.8, 1.5 times 10 to the power of 8. And this is about almost 1.5 times 10 to the power of 8. So the distance, I guess what this is trying to say is the distance from the Earth to the Sun. Well, if you were to add this is like 99.9% of the distance. The distance of the Moon to the Earth is so small compared to the distance from the Sun to the Earth that we can approximate the distance from the Sun to the Moon. I mean, it will vary, but for the most part, it's approximately 1.5 times 10 to the power of. Now we've got to convert it to meters. So instead of 8, it's going to be 1 kilometer over 1,000 meters. So instead of 8, it's going to be 11 meters. And we find our value for that. To be 4.4 times 10 to the power of 20 newtons. So now we've done Sun, Moon. Our next goal is to do the force of gravity from the Earth to the Moon, on the Moon. Gravitational constant times the mass of the Earth, mass of the Moon, all over the distance from the Earth to Moon squared. So we put in our numbers, and that would give us, we do the calculation, it gives us 2.0 times 10 to the power of 20 newtons. So let's compare this number and our number up here. Well, if I summarize it in the table, just looking at these two numbers, you can see that the mass of the force from the Moon on the Sun is roughly double that of the Moon on the Earth. But you could also divide the two numbers by each other. FG MS divided by FG mass Moon Earth, and you would see that 10 to the 20 cross off, and I have the force of gravity from the Moon on the Sun is equal to, I'm going to bring this value up, is equal to 2.2 times the force of gravity on the Moon on the Earth. So 4.4 divided by 2, okay, 2.2. So it's roughly 2.2 times the force that it will be the Moon and the Earth. So hopefully you've got a sense of how you can apply Newton's universal law of gravitation to any of the problems.